All right, let's go through a few examples with molarity. Again, this is basically an exercise in dimensional analysis, paying attention to units. With molarity, always go back to the basic equation. If let me write. Moles of solute over liters of solution. Often abbreviated, capital M is N over V. Just remember that N's moles and V is in volume in liters. Keep that straight. Pay attention to units. That's all we're doing right now, just being careful with your algebra. So what's the molarity of 2.5 moles of sodium fluoride dissolved in enough water to make a 4-liter solution? So in that case, I always start with this equation and look at what I'm given. I'm trying to find molarity. I'm given moles, which is nice. I'm given volume. And so all we're doing is just plugging in. Molarity is going to be 2.5 moles over 4.0 liters. That gives us 62.5, I think. I'm sorry, 0.625. Molarity, or molar is what it's usually called. Sig fig y is 0.63. I want to double check my math. Okay, just want to make sure. That's the basic solution. Now, where this is useful, and that's what the next part shows, is in labs we often make up a stock bottle of a known concentration. So you have a gallon or two on the shelf of, in this case, I should finish my units up here too, 0.63 molar solution of NaF. Again, M is often called, this is pronounced as 0.63 molar sodium fluoride. So if I need to have some sodium fluoride for a reaction, I don't have to go out and measure out so many grams and dissolve it and put it in my reaction. I can take my stock bottle, pour out a volume, take a graduated pipette, and measure precisely 0.358 liters or whatever I need, and I know how many moles I want to have out of there. So it makes it a really easy way to convert between volume and moles, to take a volume of a known solution and figure out and obtain so many moles of my solute. And it's actually often much more precise than trying to measure out with a spatula on scales the individual grains. You can get a little better precision there also. So how much of this solution is needed to obtain 0.1 moles of sodium fluoride? Well, let's go back to the equation. Always go back to molarity is moles over volume over liters. And I look at what I'm given. Well, the same solution, I know the molarity now because we calculated it up here. Sorry. I need to have 0.1 moles. So I really solve them for volume. So I need to rearrange this expression to solve for volume. So of course you get, and I recommend, do this yourself first. It's really easy, but people make too many careless algebraic mistakes on exams and quizzes. So practice it yourself and come back. So volume is going to be N over capital M. Therefore, my volume is going to be moles is 0.10 moles over 0.63 molar. And number-wise, this gives us 0.16. Now I'll show you the units. Moles over molarity. Well, molarity is actually moles over liters. So 1 over, the moles cancel moles. 1 over liters gives you 0.16 liters. Now here I ask how much of this solution. I did not really specify whether in liters or milliliters. I'll accept either one personally. Just take the easiest one in my opinion. We already have it in liters, no point going anywhere else. So we need 0.16 liters of solution. If I needed more or less, I just figure out a different volume. So it's much easier to figure out that way than it's much more practical using stock solutions in many cases than to have to go get spatulas and weighing dishes and figure out and measure out the exact masses that we need. So what mass of sodium hydroxide is in 200 milliliters of a 2 molar sodium hydroxide solution? Well, I'll do the same thing myself. Go back to molarity, moles over liters. And as I said, trying to find mass, we're given the volume, we're given the concentration. Well, N is moles and not mass, but we know how to go from moles to mass, so let's figure out moles. So in this case, we solve for N. Is molarity times volume, 2.00 molar, times volume, which of course is 200 milliliters, but we know that molarity is really moles over liters, so we need to get our units cancel out, or sloppy L there. So of course, milliliter to liters, 10 to the minus 3, and we get 0.40 moles. Distracted myself for a second. Anyway, because if you look at units, milliliters cancel milliliters, liters cancels the liters in molarity. Again, I abbreviated up here. And we're left with the moles up here. So that gives us 0.4 moles. Now we have to go from moles to mass. Oops, oh geez. Of course, it might help just to make sure sodium hydroxide. You should be able to figure out the molar mass of sodium hydroxide now. And that gives us, I think, 40.0. And that should be, I think, 16 grams of sodium hydroxide. And this should be it. If you're worried about units, again, I should have put in this actually moles of sodium hydroxide. Got a bit lazy there, not including that. So that's basically what we're doing, just being careful to make sure that we cancel out our units like they're supposed to be canceled. So how much water needs to be added to 2 liters of a 1.5 molar solution to obtain 1 molar HCl solution? Well, this is where we mentioned dilutions already, so I wanted to show you this in a little more detail. Back to molarity, of course, is N over V. Rearrange this. Moles is molarity times volume. Well, the moles, when you dilute something, don't change any. So the initial moles has to be of the solute has to be the same as the final moles of the solute. And that's where the relationship comes from in our initial and final units. M1V1 equals M2V2. Or some write it as moles initial, volume initial equals moles final, volume final. Same thing. Just our initial molarity times our initial volume equals our final molarity times our final volume, because both of these equal moles of solute, and that moles of solute is constant. So in this case, we just have to plug in the right values into the right constants. So I'll rewrite this down here to give us some space. M1V1 equals M2V2. Well, M1, our initial molarity, is 1.50 molar HCl. Our initial volume is 2.0 liters. Our final molarity is 1.0 molar HCl. Our final volume we don't know, we solve for V2. So work this out, pause the video, you should be able to figure this out. So V2 gives you 3.0 liters. Now, you need to ask yourself, is this actually answering the question? So V2 is the final volume of our solution. Well, the final volume is 3 liters, but we started with 2 liters. So V2 equals 3 liters equals the final volume. That means that volume added, well, final volume, think of it this way. Initial volume plus added volume. Therefore, added volume, of course, will be 1.0 liters. So again, be careful about the wording up here. How much water needs to be added? So the question isn't asking what is our final volume. How much water do we have to add to this initial solution to dilute it to get a 1 molar hydrochloric acid solution? So again, try to visualize the process. Try to visualize what's happening here. Otherwise, it's really easy to make careless mistakes on questions like this. And one quick problem to show you with stoichiometry, just to incorporate this with everything else we've covered. How much water is produced when 1 liter of a 2 molar HCl solution is mixed with 2 liters of a 1 molar strontium hydroxide solution? Sorry, this application doesn't like to do subscripts. So, like with anything else we have to go through, any reaction, let's write down our balanced equation first. HCl plus strontium hydroxide. Of course, that will produce strontium chloride. And if you look at this as a double displacement reaction, you would get HOH. We just normally write this as H2O. Then you balance your reaction. And now we need to figure out which is our limiting reactant and how much product are we forming. So, of course, we have for HCl, we know that this is 1.0 liters and 2.0 molar. Sorry, there's an extra 0 in there. So volume times concentration gives us moles. So this means we have 2.0 moles or 2.00 moles of HCl. We have 2.0 liters, 2.00 liters, and 1.00 molar strontium chloride, strontium hydroxide. So we have 2.00 moles of strontium hydroxide. So hopefully that gets you started here with solutions. Again, like I said earlier in the chapter on stoichiometry, always go to moles first. You give, in this case, we have solutions, we have volume, we have concentration. We can figure out moles. So go to moles and just treat this like a regular stoichiometry reaction. So of course, find our limiting reactant. I need to use proper significant figures. 2 moles of HCl. Moles of HCl to moles of water. 1-to-1 ratio or 2-to-2 ratio. Same thing. So this, if it fully reacts, would produce 2.00 moles of HCl of H2O. Now we have 2.00 moles of strontium hydroxide. Of course, this is a 2-to-1 ratio. We expect this to produce 4.00 moles of water. Therefore, my HCl is my limiting reactant. We use our limiting reactant. We've actually already done this calculation up here. So I'll just put this just to clarify what I've done. And we expect it to produce 2.00 moles of water. And there you go. So we can use concentrations the same way with everything else. When we do chemical reactions, write down your balanced equation, proper formulas, reactants on the left, products on the right, and convert your concentrations and volumes into moles, and we just go through the same process.